So, some videos ago, we started the proof of this long equivalence for metric spaces, right? And a metric space is compact if and only if every continuous function from the space to R achieves its infimum and supremum, and that's if and only if every continuous function for that space to R is bounded, and that's if and only if that space is complete and totally bounded. Now we're going to the next step, which is to show that if a metric space is complete and totally bounded, then every sequence in it contains a subsequence that converges to a point of K, right? So our space is K with metric T sub K, and we want to prove that these two things together imply that sequences have convergent subsequences. So that's what was called sequentially compact before. Right? Okay, how do we prove this? First of all, let's remember what it means to be totally bounded. This means that for any epsilon, K can be covered by finitely many balls of radius epsilon. So this is slightly different from the definition I gave in the previous video. It's the same thing, of course, right? So, this is just a different way of putting it. This is the same thing. As we noticed, we had this concept of epsilon natch, and then we said that by definition, K is totally bounded if it has finite epsilon natch for all epsilon. That means if the so-called epsilon covering numbers of K are finite. But as we notice, if you have an epsilon natch and you look at a closed ball centered at those points, these balls cover the whole space K. So this is really the same thing. Okay, now we want to use that and completeness. With completeness, we know what it is. It means that Cauchy sequences have to converge. And we want to use these two things together to show that every sequence has a convergent subsequence. So what I'm going to do instead is I'm going to prove that just by assuming total boundedness, every sequence has a Cauchy subsequence. Why is this enough? Well, we know that the space is complete, right? So if you have a Cauchy subsequence, that subsequence is going to converge to some x in K. So it's basically what I'm saying is that these two conditions, they play different roles. The totally bounded guarantees the existence of Cauchy subsequences. Complete means that Cauchy subsequence has to converge somewhere in K. So good. So that's the statement we're going to focus on. And how do we prove it, right? So what I'm going to present is sometimes called the diagonal trick. Some version of it is due to Cantor, the same Cantor of Cantor set and all the concepts in set theory that we've grown accustomed to. Right, this diagonal trick is really not something obvious at first sight, maybe not even at second sight or anything like that. So I'm going to present it in a piecemeal fashion, right? So we want to get a Cauchy subsequence. What is a Cauchy subsequence? It's a subsequence where terms are getting closer and closer together. I'm going to start by something weaker. I'm going to notice that for any delta positive, can find a subsequence, right? I fix a sequence x sub n, and now I take x n belonging to n, some infinite number set of indices with so I can find a subsequence x sub n such that the distance between points in the subsequence is less or equal to epsilon for all m and n. There are indices in the subsequence. Now, two things. First of all, the notation. Oh, sorry, this is delta here. The notation I use here for a subsequence is different from this, right? So here I'm saying I'm gonna choose indices n sub 1, n sub 2, n sub k, and that's a subsequence I take. X of n sub 1, x of n sub 2, x of n sub k. Another way to describe a subsequence is to take this set capital N here, not the natural numbers, this other n, and say I'm gonna throw out all the indices that are outside of this capital N and keep the indices inside the capital N. And what I need in order to have a subsequence is that this set is infinite. So that's just another way of writing things. Of course, if you have this, then you can easily write something like, if you order the elements of capital N, then these are your n sub 1, n sub 2, n sub 3, and so on and so forth. Though, I mean, that's just to give you some degree of orientation of navigating the notation. We're going to be switching to this form later, so you shouldn't think that these indices that I found in N right now are the indices I'm going to use later, because right now I'm doing something weaker than what I'd like. I'm not finding a Cauchy subsequence, I'm just finding a sequence where all terms are close together, and how close is determined by delta. Okay, so I want to prove this fact, and that's going to be my first step. So how do we do that? Well, first of all, we know that K can be covered by finitely many balls of radius, say delta over 2. Right? And why is this? So, well, I mean, it's just the definition of total boundedness, right? So I took a positive radius, and I know that the space can be covered by finitely many balls of radius delta over 2. Now, the sequence is infinite, right? So let me call these balls, well, they're closed balls, but I don't really care too much. Let me call these balls B sub 1 and B sub k. So for one of these BIs, the set, for at least one of these BIs, the set that I'm going to call N I on top, which is indices of all, and belonging to into the natural numbers, so that x of n belongs to bi, is infinite. Right, so I'm using the pigeonhole principle in this version where I have, well, finitely many holes, those are the big I's, and infinitely many pigeons, those are the indices corresponding to the terms of the sequence. So if I try to fit infinitely many pigeons into finitely many holes, one of the holes at least will end up with infinitely many pigeons. So one of these sets of indices is infinite. So what I can do in order to find my capital N is I'm going to take N to be Ni infinite, one of these infinite guys. Doesn't matter which one. And I claim I'm done. And why is that? Because if I take 2 points inside the same ball of radius delta over 2, by the triangle inequality, the distance between those 2 points is at most delta. And then I'm done, right? The triangle inequality, I'm just computing, okay, distance between 2 points in the ball is at most the sum of the distances to the middle, and those distances are at most delta over 2. So, okay, this thing here allow me to prove, right, this sort of pigeonhole principle allow me to prove this fact, that I can, for a given delta, find a subsequence whose terms are all within distance delta from one another. Okay, so far so good, but that still seems very far from being a Cauchy sequence. So what we're going to do now is we're going to try to iterate this with smaller and smaller values of delta in order to get subsequences whose terms are closer and closer together. How do we do this? Well, I need to erase some stuff. So notice that everything I used here was just total boundedness together with this infinite pigeonhole principle. or you could call it infinite to finite, right? So and now I'm going to do an inductive construction of subsequences. So the first step is what we just proved. There exists an n sub 1 containing n infinite such that for all indices n and m containing n sub 1, the distance between x sub n and x sub m is less than, I don't know, 1. That's a particular case of the theorem I stated before, except for the set of indices n is now n sub 1. Now I'm going to iterate this, and I'm going to say that I can find nk contain an nk minus 1 contain n1 such that for all I, there are one of these numbers, 1 to k, and for all m and n belonging to n sub I, let me call this j. The distance between x sub n and x sub m is less than 2 to the 1 minus j. How do I know that? Well, that really is an inductive construction. In the following sense, suppose, well, I have defined n sub 1. Now I have the sequence, right, xn with n belonging to n sub 1. And I can apply the same trick as before, right, the same principle. So I take a radius delta that's now equal to a half, right? For j equals 2, I'm going to have a half here. So take delta equal to a half. Infinitely many terms of the sequence x sub n with n and n1 have to belong to some ball of radius a quarter, right? A half of our delta. Delta is equal to a half, right? So these are like, let me call these delta sub j. So I'm looking at delta 2, which is a half. And by applying the same trick as before, I say, okay, infinitely many elements of n sub 1 are such that the corresponding points of the sequence belong to the same ball of radius delta 2 over 2. And therefore, I can find a subsequence of n1, right, an infinite set of indices contained in n1, such that the distance between any two guys is less than 2 to the 1 minus, well, 2 to the 1 minus j, j is equal to 2 in this case, so less than a half. Now you can continue, right? Suppose I have built this guy, and in here, all distances are less than 2 to the 1 minus k minus 1. I can apply the same trick again. So I have a sequence x sub n indexed by this set n sub k minus 1. And I know that I can find infinitely many terms of this guy with n sub k within distance 2 to the 1 minus k from one another. So I keep doing that. And of course, that gives me an infinite sequence of sets, right? So for each k, I have a set like this. So in fact, for all, if I want, I can write it like this to just say, if I iterate this construction forever, for all j in n, if I take two terms in the subsequence n sub j, or the infinite set of indices, right? So I forgot to write this, but all these guys have to be infinite sets of indices because I want subsequences, right? And for subsequences, I need infinite sets of indices contained in the natural numbers. Now, for any one of these sets of indices, if I look at m and n belonging to the set, the distance between the corresponding terms of the sequence is less than 2 to the 1 minus j. Okay, so now I have all these indices and so what, right? So I still don't have a Cauchy sequence. What I do have is like a nested family of subsequences, right? So subsequence n sub j is contained in subsequence n sub j minus 1, which is subsequence of n sub j minus 2, and so on and so forth. And these nested subsequences are such that for each one of them, the maximal distance between any two elements of the sequence is getting smaller, right? As you go down in this hierarchy, right? So now I want to find a subsequence. And my subsequence should be, I'm going to choose the indices from these sets somehow to get what I want, my Cauchy subsequence. How does that work? I mean, okay, maybe one thing you could do is you're saying, okay, since these guys are getting better and better, in the sense that the corresponding terms of the sequence are getting closer and closer. Maybe I should take the intersection of all these sets, and that's going to give me the set of indices of my subsequence, the final subsequence. Well, it turns out that that trick in general does not work, and maybe it's a good exercise for you to think why you shouldn't take the intersection. And here comes Cantor's diagonal trick. So he defines n sub 1 as the smallest element of n1, and he defines n sub j as the smallest element of n sub j if we remove the guys that you have already chosen. So it's another inductive construction. Right, so you define these indices and you notice that they are increasing, right? So because, for instance, n2 is the minimum of the set n2, but I removed n1, so it's got to be a larger element, right? So, so here I should write something different. I should remove all numbers from 1 to n sub j minus 1. I mean, actually it doesn't matter, but it makes life a little bit easier if I do it like this. So I'm making sure by removing these elements that n sub j is bigger than n sub j minus 1. And by the way, how do I know that I can remove all these guys and still have an empty set, right? So I'm using here the fact that any non-empty set of the integers has the smallest element, or any non-empty set of the natural numbers, has the smallest element. How do I know that the set is not empty? Well, it's simple, right? This guy is infinite. So if I remove finitely many elements, I'm still left with something. In fact, I'm still left with infinitely many things. Okay, so I have these guys, and I claim that the subsequence indexed by them is Cauchy. So this is the object that I need to look at to finish my proof. How does it work? Well, it's actually quite simple. Notice that for all J1 and J2 and N, let's say that J1 is less than J2, or less than or equal to. Let's look at this, right? So NJ1 belongs to capital NJ1, and J2 belongs to capital NJ2, which is contained in NJ1 by our nested construction, right? So NJ2 is the smallest element of capital NJ2 once I remove a few things, so it belongs to NJ2, which is contained in NJ1. And what do I know? I know that if I take two indices in NJ1, the distance between the corresponding terms of the sequence is less than what? Well, if I have two guys in n sub j, the distance is less than 2 to the 1 minus j. So if I take two guys in nj1, the distance is less than 2 to the 1 minus j1, sorry. So this is when j1 is the smallest one. In general, you can forget about this and just, reversing the roles of j1 and j2, have the minimum of the two guys here. So what does that mean? Look, I want to prove that the subsequence here is Cauchy, right? So what do I need to show? That the distance between terms x, this is the term j1 of the sequence and the term j2 of the sequence, this distance should go to 0 when both j1 and j2 go to infinity. But now I have an explicit bound, right? I'm saying this distance, it's non-negative, if you like, and it's less than 2 to the 1 minus the minimum of j1 and j2. When both j1 and j2 go to infinity, this minimum goes to infinity as well, and 2 to 1 minus that goes to 0. And therefore, I can see that this distance goes to 0 when both j1 and j2 go to infinity, and I'm done, right? So because that's precisely the Cauchy property. So the sequence here, indexed by j, given by x sub n sub j, is a Cauchy sequence because when I evaluate the distance between x sub n sub j1 and x sub n sub j2, and I take j1 and j2 to infinity, this distance goes to 0. What did I achieve? Well, what I did was I finally found a subsequence that's Cauchy As I noted before, a Cauchy subsequence has to be convergent because the space is complete. Therefore, I'm done. I've proven the theorem. Okay, just to recap, right? So what have we done? It's, I mean, this is a bit, I don't know. When I first saw this proof and I finally wrapped my head around it, it felt like I don't know, had been walking, I don't know, in the desert, and I suddenly found an alien tool, something I couldn't quite understand, but I mean, I fiddled with it a little bit, and then it sort of made sense, but still sort of mysterious proof, right? So again, what's the idea? And the idea is this. So we decide that we want to find Cauchy subsequences, and the main point is that given a sequence or maybe a subsequence of the original sequence, you can always find a subsequence of that subsequence where all terms are close together. And by close together, I mean their distance is less than, say, 2 to the 1 minus j. So since you can do that to the whole sequence or to subsequences of the whole sequence, you iterate that. So at the first level, you guarantee that everybody's within distance 1. At the second level, everybody's within distance a half. At the third level, everybody's within distance a third. And you iterate, right? So you're getting sets of indices that are contained in the previous ones, all infinite, and now with this increasing closeness. But now at the end, you have to find a single subsequence, and this is a diagonal trick, right? In some sense, what Cantor noticed is that you have n1 and then a bunch of stuff, and maybe you have n2 and some elements, and then n sub 2 and 3, some other elements and 3. So what Cantor looked at is what if we pick guys like this? So we make sure we pick one from each level, that we're moving to the right so that the terms are increasing, right? So I need them to be increasing because I want these indices to be different. I want to have a subsequence. So I have taken 1 and 2 that's greater than 1 and 3 that's greater than 2. And this is guaranteed by this construction. And I also want one from each level because as I move down the levels, I know that the terms are getting closer and closer. And this is what we have over here. Distance of x sub n j1, sub j1, x sub n sub j2, is less than 2 to the 1 minus the minimum of J1 and J2. With this, we have achieved what we wanted. We found a Cauchy subsequence. And with that, I'm going to stop. And, well, in the next video, we're going to finish this proof of all these equivalences. And this, of course, a major step. So, thank you.